So welcome you all to today's last session. The session focuses on post-quantum cryptography. And for this session, we have as a session chair, Professor Bert Bollens and Dr. Kusum Ladda. And one more announcement during the session, you can directly give the question answer to the authors through the QA link that is there in the event platform. So over to you, to the session chairs.
Sorry, I was on mute. So, welcome everybody to the third session. This session is about post-quantum cryptography. We have 3 papers for you. And the first paper is called DEC-side, Delegating Isogeny Computations in the C-side Setting. This is a paper by Robbie Peterson, and Robbie will give the talk. So, Robbie, please go ahead.
Can you see the presentation?
Yes, but it's not on full screen yet.
Yes. All right. So thank you very much. So I will talk about isogeny delegations in the C-side setting. As Walt already introduced me, I'm Robbie Peterson. So isogeny-based crypto is now about 25 years old, and in the last 10 years, 2 schemes have been proposed that are that seem to be post-quantum secure, and we generally call them SIDH and C-side. And isogeny-based crypto has this big advantage that it has very low public key sizes in comparison to other post-quantum schemes, but unfortunately, isogeny computations are quite expensive. So the goal of our presentation was basically, or our paper was to use delegation models by Hohenberger and Lizanskaya to allow parties to outsource these computations. And I will first introduce how these delegation models look like. So basically, the idea is we have a trusted we have a central party, which is the delegator, who we assume is computationally restricted and wants to outsource its computations to some other entity called server. And we assume the server will be computationally quite powerful, so that T can send queries to the servers and get responses in return. And basically, every other entity we have in this scheme is called the environment. And we assume the environment to include the manufacturer of the server U. So there might be some collusion between the environment and the server. And also we can assume that the server can be maliciously programmed. But the environment also includes all the parties that interact.
Robbie, sorry to interrupt, but we're still seeing your first slide. Is that the intention? Probably not.
No, I'm sorry. Then I will try it again. Excuse me. I'm very sorry. Can you see it now? Wait, when I switch?
Yes, now.
Okay, I'm very sorry, then I'll put it on full screen again. All right, so yeah, I will skip the slide. So this was just about the introduction of isogeny-based crypto and the delegation model. And the general idea of the delegation model is that we have this computationally restricted device called the delegator, which we denote as T. And we assume this delegator to be able to interact with some computationally more powerful server by sending queries and by receiving responses. And every other party, as I said, is generally called the environment, and the environment can includes the manufacturer of the server and might therefore collude with the server or might maliciously program the server. But we also assume that the environment includes all the entities that interact with the delegator T. So the environment might also influence whatever queries T sends to the servers and might also listen to whatever T chooses to publish in the end. And in this paper, we will always use the assumption that we have 2 such servers so that T can interact with both. So both might also be maliciously programmed, and both might even maliciously collude. But the very important assumptions of these delegation schemes is actually that when T starts using U, T can basically install you behind some kind of firewall so that the environment does not have a direct communication channel to these servers anymore. They might still be maliciously computed or designed, but there's no direct communication channel anymore. And similarly, both servers can also be chosen to not have a direct communication channel anymore. So the actual interactive scheme looks as follows. And we can assume that that E and U might still try to send each other sensitive data via the in and outputs of T, but have no direct channel anymore. And we will look at two assumptions in this talk. One is called the two honest but curious model, where both servers are assumed to always respond with correct results, but they might still try to learn something sensitive about the secrets of T. And the other scheme will look at where one server is potentially malicious, so might also respond with wrong results, but the delegator does not need to know which one it is. And so basically this is called a one malicious but two untrusted program model, or OMTAP for short. And I will quickly introduce isogeny-based crypto in the C-side setting, but instead of formally defining it, we can just think of this as a group action. So we can think of a group G acting on some set E by the action which we denote at star. And let's say we have some set E, and what this means is that if we have a starting element, so in this case, an elliptic curve E, and if we perform some action on it, we will just reach another elliptic curve in this setting, in this set, sorry. And if we have a different isogeny, for example, B, then we will also go to a different elliptic curve. So these are uniquely defined. And so the hardness assumptions underlying this group action is basically can basically be summarized as vectorization and parallelization. So vectorization is given two random elliptic curves or two elliptic curves that are far enough apart. It is very difficult to find the isogeny connecting them. And the other one is parallelization. So even if we have two elliptic curves E and E prime connected by such an A, where the A is unknown, then it's also difficult to act on some F with A. So we can also do that, and this is called parallelization. And as already said, so in C-side, this set E is a set of supersingular elliptic curves over a prime field, where usually we take P to be 3 mod 4. And G is the ideal class group of the endomorphism ring of these elliptic curves. And what this means is that basically we can think of isogenies as being defined by the kernel of ideals. And also in these settings, the underlying prime P is usually chosen to be a multiplication of a lot of small odd primes and then -1. And these small odd primes then generate low degree isogenies. And low degree isogenies are very efficiently computable. So this is how we can make this actually worthwhile, in the sense that that we have low costs of computing these isogenies. And each L basically defines some isogeny in one direction, but also its dual in the other direction. And since these isogeny paths are defined on each element of the set, we can basically see L1 in this case as spanning the entire graph. And similarly, L2 spans the entire graph, and so on and so forth. And what's great about this is that we can now, let's look back at our isogeny we had before. So A, we can now decompose A as small degree isogenies. And in this case, we can, this would be two consecutive applications of L1 and then an application of L2. And this is in general true. So we can take any element and always decompose it as these small isogenies, these prime isogenies, just like we can decompose any number into prime factors, basically. And what's also good is that since these Li are public, so they're part of the prime P, we can also just express this action by using the vector in the exponent. So where A1 is the exponent of L1, A2 of L2, and so on. And so in our example in the bottom right, we would have a vector which has 2 as the first entry, 1 as the second entry, and so on. And this is already enough to generate Diffie-Hellman schemes. So basically, since it is difficult to infer the isogeny just from getting two elliptic curves, Alice can have her secret isogeny A, compute the codomain EA, and this is then a public key. Bob does the same with EB. And now both can use each other's public key, and then again act with their own isogeny, and then they will end up with the same elliptic curve, which is then used to compute their shared secret. And diagrams like these, we will generally simplify them as seen on the right here. All right, so there's one more thing. So we need to know the class group. So now I said we need elements from the class group, but computing class groups is actually quite a difficult task. So we cannot always assume to know it. So there's some parameter sets for which it is known and some parameter sets for which it isn't. So if the class group is known, we also assume that we know some generator of it, and we also know the relation lattice. And so what we can do if you want to sample a random element when the class group is known is just to sample a random integer. And then we use the relation lattice, and then we use the generator to the power of this integer. And then we use the relation lattice so we can express this as these small prime isogenies. But if the class group is not known, we thankfully know approximately the size of the class group. So what we do instead is, instead of sampling an integer, we just sample these vectors immediately. And this can be usually be done by sampling from some specific box so that the computation cost will not be too high. And this box that we denote here as bold B has then to be chosen to cover more or less the entire class group. All right, so what do we want our servers to do? So basically what we want to be able to do is give our server some similarity curve E and some representation of an isogeny A, or of the ideal underlying the isogeny. And again, we distinguish the cases where we know the class group and where we don't. So if the class group is known, we can just sample a random integer again, and then just give this integer to the servers, and we assume the servers do take the generator to the power of the integer and use the relation lattice to compute the group action. Otherwise, we just give, if the class group is not known, we just give A, so the vector, to the servers, and then they can immediately compute the group action. And we also assume that we can give multiple such queries at the same time to each server. And then we get an ordered list of the results. All right, so for the cryptographic protocols, we have to think of 3 different types of delegations that we need to know. So assume again, we have some elliptic curve E0, and we have an isogeny S that we want to delegate, and we have a codomain S times E0. And now we look at different factors where we look at which one is public and which one is hidden from the servers. So the simplest case is that S is simply public, and the codomain is also public. So what we do is we just give all the information to both servers, and then we compare the results if they are the same in the OMTAP case, and then basically we're done. So that's the trivial case. If you want to hide S, it becomes a bit more difficult, but the idea that we do in the paper is to basically decompose A into 2 separate ideals or separate isogenies. Then we delegate the first one to the first server, then the second one to the second server, and then the codomain should be correct. And if you also want to hide the codomain, then we do a similar approach. We decompose S into 3 elements. We let the servers compute the first and then the second, and then basically we as a delegator, we compute the third part. And of course, it's important that this third part is still large enough so that the server cannot just guess the codomain curve, but it also needs to be small enough so that the delegator does not have to do too much computation. So for the rest of this talk, I will talk about how to decompose these elements into 2 or 3. And I will also talk about how small this A3 can be so that it's still secure, but that it's still computationally worthwhile for the delegator. Something I will not cover in this talk is how do we verify OMTAP, the correctness in the OMTAP assumption. So if one of the servers is malicious, how can we make sure that these results are actually correct? And this will be covered in the paper, but I don't have time to go into details here. All right, so how do we decompose a vector? So if the class group is known, this is very, very simple. This is done similar to the D-log case, where we just split up A into 2 elements, and these 2 elements generate 2 separate isogenies that together actually generate S. So we can just basically take our S and define it as A1 plus A2, and then we have 2 separate isogenies. But in the case where the class group is not known, this is a bit more complicated, unfortunately, and I will just illustrate this with an example. So if we try to do the same approach, let's assume we have S, which is sampled from some box B from -5 to 5. Now, if you would sample another element, R0 from this B, and then create the difference, you would have the problem that a lot of elements are actually not in this box anymore. And unfortunately, this means that we will leak information about the secret. So what we do instead is we sample from a bigger box. And this means we scale the box by some factor delta, which here as an example is 3. And then R0 is from a bigger set. And then if you compute R1, we will have less elements outside the box, delta B, but we will still have some elements. So what we do now is we define R star. And on every place where we're outside the box, basically, we define R star to be S, and we define R1 to be the negative of R0. And we do this for all the other terms that are outside the box, and the rest we just set it to 0. Now R1 is actually in the box by design, and R star is a very small vector, so small in terms of Hamming weight. And their sum is actually exactly S. And this is what we call the short vector algorithm. So if we look at this in the picture, basically we have we decompose the isogeny we want to hide by giving U1 the first, so R0, for example, computing R star ourselves, and then giving U2 the computation of R1, and then we will arrive at the correct codomain curve without disclosing S. And R star is also chosen to be in the middle of these two curves in order to avoid isogeny recovery attacks. And basically bigger delta means we have a smaller R star, so also in terms of Hamming weight again, but we will have more communication cost. And in the asymptotic limit, actually, this Hamming weight will vanish. And the other splitting, so this is the short vector algorithm, and then we also had the splitting algorithm. And the splitting algorithm is what we need to be able to hide the codomain curve. And the idea is a bit similar. So we take a vector S, and then we define S star, and we just give it some random values of S at the correct positions, and the rest we will set to 0. Then we define S prime as S minus S star. So S star plus S prime will become S. And S prime is obviously still in the box. And what we can do now is we shroud S prime. So our current picture will look like this. So we have our S now split up into 4 elements. We let the computer compute, the first server compute R0. We compute R star ourselves, and then we delegate R star, and then we compute S star ourselves. And in this way, S star will never be disclosed to the servers, and then only the delegator will know it, and only the delegator will know the codomain curve. And the question again is, how big can we choose this S star? And actually, we can also express this in terms of the Hamming weight. So we just want to make it impossible for a server to guess S star from all the possible choices. So if the Hamming weight is K, then we have this formula in the bottom right that says we have to choose K as big enough so that randomly guessing S star is at least as difficult as inverting some isogeny. So computing and figuring out an isogeny by an isogeny recovery attack. And so just to quickly summarize, so if S is public and the codomain is public, we can just immediately delegate it. If S is hidden and the codomain is public, then we go via this detour. So here, shroud vector in the case where the class group is unknown. If the class group is known, this is a bit easier. We don't have this R star in the middle. And finally, if we also want to hide the codomain, then we do it as I just presented to you, and we compute R star and S star ourselves. So the cost of the delegator will always be reduced to computing R star and S star, basically. And these are our results. So what you can see in this table is basically the cost of the delegator compared to to the undelegated cost, so to the actual protocol cost. So if you look at the very first number, we have C-side 512 in the 2HPC case, and if we choose delta equals 1 even, we get 46% of the original cost. So we get a reduction by a factor of about 2. And this increases with higher delta, but then the communication cost also increases. And in the asymptotic limit, we can reduce C-side by a factor of 9. And this asymptotic limit actually also coincides with the case where the class group is known. So if you know the class group, which is the case in C-side 512, we can reduce its cost to a factor 9. And in C-side 496 or higher parameters in general, we get even a higher reduction, but we don't know the class group in these settings. So we can more look at delta equals 5, delta equals 10 to be realistic estimates. So we have a reduction to 10 to 7% of the original cost. And finally, in signature schemes, the results are even better because we do not have a hidden codomain in the signature schemes. So we never have to compute the S star ourselves. And we can see in the asymptotic limit of C-side 512, we actually go below 1%, so around 0.3% of the original cost. And in C-side 512, so for the C-side 512 parameter set, the class group has been computed in the C-fish paper. And basically, this means we can reduce CFISH to below 0.3% of the original cost. And that's already it. Thank you very much.
Okay, thank you, Robbie. So I'm waiting for questions to reach me, but in the meantime, I can ask a question of myself. So yeah, as you mentioned, in the case that you want to hide the codomain, then you split up this S in an S prime and an S star. And this S star is chosen by taking some coefficients from S and putting the others to 0. But yeah, to me, it seems that the only thing you care about is that this S star is unpredictable. So would it not be more efficient and more natural to just pick an S star from a small box instead of doing it this way by choosing only a few coefficients? Just pick a random S star from a small box.
Yes. Do you still see my slides?
No, I don't think so.
But I can also just try to explain it like this. So we initially also worked with this. This also actually works, and the results are quite similar. But it turns out we have two problems. So if we define this S prime as this S minus S star, then we sometimes fall out of the box. So we have this problem again. So that's one of the two things. And the other one is that actually, so the way of guessing the vector is then that the server will guess in the smaller box. And actually for, so we have to choose different parameters. And actually for C-side 512, if I remember correctly, we had a difference of about 2 or 3% less efficiency. So it's not a big difference. So it's definitely possible, but just this design was a bit cleaner. And this is why we choose to use this one. Yeah.
Okay. Thank you.
But it definitely works. Yeah.
So are there any questions from the audiences now? Is there any question? Side? No. Okay, so there are no questions from our side.
Okay, then I propose we move to the next paper.
Thank you.
Yeah, thank you, Robbie. So the next paper is Key Oblivious Encryption from Isogenies with Applications to Accountable Tracing Signatures by Shurbi Shah and Ratna Dutta. And I believe Shurbi will give the talk. So if you're here, please, the floor is yours.
Yes. So is my screen visible?
Yes, we see your screen.
Okay. So hello everyone, I am Survi Shah. Today I am going to present our work on key oblivious encryption from Isogenies with application to accountable tracing signatures. This is a joint work with my supervisor, Dr. Ratna Dutta. So we'll see what is the key oblivious encryption and why should we care. So recent interest in designing such primitive is because of its application in designing accountable tracing signatures. Now, what are accountable tracing signatures? I'll come to that in a moment. Also, key oblivious encryption is useful in designing anonymous credential systems where key privacy is the prime concern apart from data privacy. Also, key oblivious encryption is an independent primitive and can be used to design several other privacy preserving protocols. This has been developed already in the lattice world, but it wasn't explored much in the isogeny world, so we believe it is worthwhile to develop such a primitive in the isogeny world using isogenies. So before seeing what's an accountable tracing signature, let's first recall what's a group signature. So a group signature allows a member of a group to sign a message on behalf of the whole group. And there are two fundamental properties of a group signature. First is anonymity, which ensures that any computationally bounded adversary will not be able to guess the identity of the signer who has signed the message. The second is traceability, which ensures that any valid signature can only be opened by the group manager and no one else. So the problem with this traditional group signature is that we are trusting the group manager blindly and there is no means we can check the accountability of the group manager. So in an accountable tracing signature, a group manager is kept accountable for his actions. So once a group user enrolls in a group, the group manager fixes the category of the user. One class of users are traceable users. These are the suspected user, and for which the anonymity of the users can be revoked at any point of time by the group manager. Another class of users are the non-traceable users, and their anonymity remain preserved, and the group manager cannot trace who has signed the message. So the group manager issues certificate for each of these users based on the category traceable or non-traceable. Also, the group manager generates a witness corresponding to the category he has chosen. So at a later point of time, the group manager will use this witness to enforce his accountability. So in an accountable tracing signature, similar to group signature, a member of a group signs a message on behalf of the whole group, and a verifier checks the validity of the signature. So if it's a valid signature, the group manager can now open the signature only if the signature is signed by some traceable user. So the group manager outputs the public key of the signer who has signed the message and generates a proof. The judge algorithm checks that indeed the signature sigma has been signed by the signer S. And finally, the account algorithm checks the accountability of the group manager. It uses the witness and checks that whether the category chosen by the group manager corresponds to the witness. So the main building block in designing accountable tracing signature is key oblivious encryption. So we can say that key oblivious encryption lies at the heart of such a primitive, and that is why we are so much interested in designing a key oblivious encryption first. Let's recall the definition of a public key encryption. So suppose Alice and Bob wants to communicate over an insecure channel securely. So Alice encrypts her message under Bob's public key and generates the ciphertext CT. Bob can then decrypt the ciphertext using his secret key SK and get back the message M. Now, in a key oblivious encryption, there is another algorithm, Keyrand, that randomizes the public key PK of Bob into some new public key PK prime. Now, this time Alice encrypts her message using PK prime and not PK. But Bob can decrypt the message, the ciphertext CT, using his secret key SK, which was corresponding to PK, and get back the message M. So this is basically the prime difference between key oblivious encryption and public key encryption. So in case of multiple users can then randomize the public key PK of Bob into some new public key PK1, PK2, PK3. Then they can encrypt their message M1, M2, M3 using this randomized public key and generate the ciphertext CT1, CT2, and CT3. Now Bob can decrypt each of the ciphertext using his secret key SK corresponding to PK and recover the plain text message M1, M2, and M3. So more precisely, a key oblivious encryption allows a large set of public keys all related to the same secret key. So as here we can see, the PK1, PK2, and PK3 here are all related to the same secret key SK. Next, the existing public keys can be randomized to generate related keys, as in here PK has been randomized to generate PK1, PK2, and PK3. It cannot be differentiable that how these public keys are related unless we have the knowledge of secret key and the randomness used in the generation. So there are three security requirements for this primitive. First is key randomizability. Second is plain text indistinguishability under key randomization. And lastly, key privacy under key randomization. So we'll look at it one by one. We'll start with key randomizability. So this is an experiment between a challenger and an adversary. The challenger generates a public and secret key pair. It randomizes the public key PK using some randomness R and generate a new public key PK naught. It again runs the Keyrand algorithm to generate a fresh public key and secret key pair PK1 and SK1. He flips the coin and sends the public parameter, the public key PK, and one of the public key PK naught or PK1 to the adversary. The adversary now needs to guess the bit B. The second security game is plain text indistinguishability under key randomization. the experiment between a challenger and an adversary, where the challenger generates a public key secret key pair. It gives the public parameter and the public key to the adversary. The adversary randomizes the public key pk into some new random public key pk prime. It gives the randomized public key pk prime along with the randomness used for its generation, along with two messages m0 and m1 and the state information to the challenger. The challenger checks if this randomized public key has been computed correctly. He flips a coin and encrypts one of the messages m0 and m1 under this randomized public key pk and gives the ciphertext CT to the adversary. The adversary has now to guess which message m0 and m1 has been encrypted by the challenger. And in the last security game is key privacy under key randomization between the challenger and an adversary, where the challenger generates two pair of public key and secret key and gives both the public key and the public parameter to the adversary. The adversary randomizes both these public key and generates new pair of public keys pk0 prime and pk1 prime. It gives both these randomized public key along with the randomness used and a message and the state information to the challenger. The challenger checks if these public keys, randomized public keys, has been indeed correctly computed. He flips a coin and he encrypts the message M under one of these randomized public key pk0 prime or pk1 prime and gives the ciphertext CT to the adversary. The adversary now has to guess which randomized public key has been used to encrypt the message M. So before seeing our key oblivious encryption scheme from Isogenies, we'll just briefly go see the necessary background and preliminaries of elliptic curve and Isogenies. Much of the background has already been covered in the previous talk, but let me just recall it once so that ones who has missed the previous talk can follow. So we'll start with the definition of elliptic curve. An elliptic curve over the field K is a non-singular projective cubic curve, and the set of all K rational points forms a group. By K rational point, I mean the points on the elliptic curve, the coordinate of which belongs to the field K. An isogeny is nothing but a morphism between two elliptic curves that preserves the point at infinity. Now here's an important theorem that states that an isogeny can be identified by its kernel. So once we have an elliptic curve E and a finite subgroup H of it, then there exists a unique elliptic curve E prime and up to isomorphism, a unique isogeny connecting them such that the kernel of this isogeny is the subgroup H. And Velu's formula gives the explicit formula how to compute this isogeny and this codomain elliptic curve. Now the underlying structure of most of the isogeny based primitive is a class group action. So for that we need a group and a set. So the group is going to be an ideal class group and the set is the set of all FP isomorphic classes of supersingular elliptic curve whose endomorphism ring is z root over of minus p. So there is a reason why we choose such an endomorphism ring. Because such elliptic curve with this endomorphism ring can be uniquely identified by its Montgomery coefficient. Now we'll see how this group action actually works. So we sample an element from the ideal class group. A member of ideal class group is written in this manner in Gothic letters with third bracket as it represents an equivalence class. Now we consider the subgroup by considering the intersection of all the kernels of the endomorphisms lying in this ideal. Now, using the theorem I have stated before, once we have elliptic curve and a subgroup HA of it, we can now define the elliptic curve E quotient HA and isogeny, connecting them using Velu's formula. So this is how the group action actually works. Now we are ready to see our construction of key oblivious encryption from isogenies, which we have referred to it as commutative supersingular isogeny key oblivious encryption. So we'll start with the setup algorithm. We choose a prime of this form 4 times L1 L2 Ln minus 1, where these Li's are small distinct odd primes. We set an integer m, a base elliptic curve E0, whose endomorphism ring is z root over of minus p. We define a function that maps an elliptic curve to its Montgomery coefficient. We sample a hash function and set the message space to be this. So this is our public parameter. In the next keygen algorithm, we sample two elements from the ideal class group. So sampling an element from the ideal class group, we sample two integer vectors of length m and whose coordinates belong to this range minus m to m. We pick the vectors from this range to reduce the computation cost. And so these two vectors define the ideal class group element A and R. Now we compute the action of this A on E0 and generate a new elliptic curve E1, and E2 is obtained by computing the action of this ideal class group element R on E1. So this is actually computing the action of A on E0 followed by the action of R on E1. So our public key PK is this new public key elliptic curve E1 and E2, and the secret key is the vector R. Now the Keyrand algorithm randomizes the public key PK. So we sample another element from the ideal class group. For that we sample element vectors of length m, whose coordinates belong to this range -m to m. Now we compute the action of this random element from the ideal class group on E1 and E2 and generate new set of elliptic curves which comprises a randomized public key PK prime. To encrypt the message, we sample an element from the ideal class group C. For that, we sample an n-length integer vector as before. We compute the action of this ideal class group C on E1, which is our CT1, and CT2 is a hash of the Montgomery coefficient of the elliptic curve computed by the action of ideal class group C on E2, XORing with the message. So this is our ciphertext, and to recall the message, we compute CT2 XOR with the hash of the Montgomery coefficient of the elliptic curve computed by the action of R on CT1. So the correctness of our scheme follows from the commutative structure of the ideal class group, and also for the fact that Montgomery coefficient gives a unique representation for the elliptic curve. So there is the underlying hard problem for our scheme. It says it's the commutative supersingular decisional Diffie-Hellman problem, which states that it is hard to distinguish between this tuple E0, AE0, B0, and ABE0, and some random tuple E0, A0, B0, and C0, where A, B, C are random elements chosen from the ideal class group. So these are the three security theorems which we have proved in our paper. Under the CSSDDH assumption, our scheme satisfies key randomizability. Our scheme satisfies plain text indistinguishability under key randomization, under CSSDDH assumption, and the assumption that the family of hash function is entropy smoothing. And lastly, under this assumption, our scheme satisfies key privacy under key randomization. So in summary, I'd like to say the main goal is to construct a key oblivious encryption that is secure against quantum adversary. We have shown an instantiation of our work using C-side 512 parameter set. We have shown our scheme to be secure under the three security models I've discussed. As an application to our key oblivious encryption scheme, we have developed an ATS accountable tracing signatures based on isogenies. I haven't covered that in this slide. For the interested viewers, I'd request you to refer to our paper. And lastly, in the future, it would be desirable to see more privacy preserving protocols that can be built using key oblivious encryption. Thank you for your attention.
Thank you very much for the nice presentation. So, maybe first, are there questions in the room?
So is there any question? Do you want to have any questions, sir? Okay. Okay. Question? Okay. So there is no question from the audiences right now.
Okay. I have a question. So, you didn't really discuss during the presentation, but to build your accountable tracing signatures, you use non-interactive zero knowledge proof. And I was wondering, do you think there's like an efficient way to instantiate this zero knowledge proof, or do you have to use some kind of generic?
Yeah, we have used some generic proof, and it is not very practical and efficient, but we still believe that it serves to advance the state of art of post-quantum settings.
But yeah, do you believe there's hope of finding an efficient, like specific zero knowledge proof for your relation?
Yes, we are working on it, and we would like to do it in the future, the zero knowledge proof part.
Okay, that's interesting. And also, yeah, you mentioned that there might be other applications for the key oblivious encryption. So is there,
Yes.
can you tell us something about that?
So, many primitives where the key privacy is the prime concern, apart from data privacy, like in anonymous credential systems or like in anonymous broadcast encryption, bit secrecy. In that areas, there had been applications for key oblivious encryption,
Okay.
where we look for the key privacy more than data privacy.
Okay, thank you very much. So I suppose we move on to the last paper of the session, unless there's more questions. No. So yeah, the last paper is identity-based signatures and an extended forking algorithm in the multivariate quadratic setting. It's a paper by Sanjit Chatterjee, Kanksha Dimri, and Tapas Pandit. And Tapas will give the talk. So please go ahead.
Am I audible? Hello. Am I audible?
Yeah, we hear you.
Okay. Can you see my screen?
Yes.
Good evening, everybody. This is Tapas Pandit. Title of this talk: Identity-based signature and extended forking algorithm in the multivariate quadratic setting. This is a joint work with Professor Sanjit Chatterjee, Akanksha Dimri. So first, multivariate quadratic system, in short, MQ system. It is nothing but a collection of M quadratic polynomials in n variable. So expression of this quadratic polynomials is here. So these are the coefficients. Coefficients come from a field F. MQ problem: given a random MQ system P and a random point Y, find an X such that Px equal to Y. So this problem is believed to be quantum safe. In the MQ setting, mainly signature schemes are studied. Recently, they have got popularity in the crypto community. The schemes like Rainbow, LUOB, MQDSS were shortlisted for the second round of evaluation for NIST PQC project, and Rainbow is one of the finalists. Salted EOB signature proposed by Sakumoto et al. For giving security reduction for EOB signature. Keyrand algorithm. So here H is a cryptographic hash function from M cross 001 to L to FM. So this is called salt space. And public key secret key generated in the following manner. First, choose random central oil vinegar map F from FN to FM. So this is again a specialized specialized quadratic system. So specialized in the sense that given any random target, so it can be solved efficiently. Pick any random invertible affine map T from Fn to Fn and set public key to be F composition T, and secret key is just a tableau information, that is the F and T. Sign algorithm takes message and the tableau information, that is F and T, and signature generation is shown by this red color arrow. For a message M, choose a random salt, then compute hash, that is the digest is Y, then solve the system F for this target. If solution is available, then proceed with the solution. Otherwise sample new salt. Let X just be the solution for this F system, and then apply T inverse to get X. So here signature has two components. One is this X and other is salt S. And signature verification you can see by this blue color direction. Just compute this P of X and also compute this hash of M on M and S, that is a Y. If they are equal, then accept, otherwise reject. Under the hardness of WM2 problem, also known as EOB inversion problem. So this EOB, salted EOB, is EOB CMA secure in the quantum random oracle model. Sorry, classical random oracle model. Now we'll briefly discuss 3-pass IBIS of Sakumoto et al. So Keyrand will give public key secret key. So here Secret key is X, so X is chosen from randomly from Fn, and public key is a random map, quadratic map, and Y is computed as a P of X. Interaction between prover and verifier uses a commitment scheme and polar form representation of the public map. Here, provers input public key secret key and verifier input public key. In the interaction, prover essentially convinces verifier that prover knows the underlying secret. At the end, a proof is generated. So proof pi has three components: commitment, CT, challenge CH, and response RS. So here I point out that prover has actually two parts, P1 and P2. P1 is responsible for generating this commitment part, and P2 is responsible for generating this response part. This 3-pass IBIS has three special soundness: statistical, honest, verified, zero knowledge, and 2/3 knowledge error if underlying commitment scheme satisfies computational binding and statistical hiding. Here, three special soundness means given three accepted proofs with condition that challenges are different, then we can define some extractor which will give you the secret key or witness. If the IBIS is run R times in parallel, we refer to this IBIS as IBIS R, and in this case, knowledge error will be 2/3 to R. Security model of IBIS, so it is defined as an interactive game between a challenger and an adversary. Challenger first provides public parameter to the adversary, and adversary also given access to a key oracle and a sign oracle. And at the end, adversary will submit a forgery, that is a sigma star on n star ID star. Advantage of this adversary in this game define that with the probability that this is valid, and ID star has not been asked to key query, and n star ID star has not been asked to sign query. We say that scheme is UF CMA secure if this is negligible, and a weaker version called UF CK security. So in this case, sign oracle is not provided, and further weaker version called UF NMA security. In this case, no oracle is provided. So in the literature, there are very few IBIS construction available, but none of them are very much. Either they are inefficient or do not have formal security reduction or correctness. Further, it is not clear whether generic construction of Bellare et al. Based on the standard identification can be applicable or instantiated in the MQ setting. So therefore, we are looking for probably secure efficient construction. So here is our proposal on probably secure IBIS. This is based on salted UV of Sakumoto, 3-pass IBIS of Sakumoto, and Fiat-Sumi transformation. First IBIS setup. So just simple run keygen of salted UV to generate public key and secret key, and two hash function. So this is not, H1 is nothing but the hash function that is involved in salted UV, and this is something called Fiat-Sumi hash to convert interactive to non-interactive one. Proof from interactive to non-interactive. And R denotes number of rounds, and public parameter is just this information, and MS key that the tableau information. Now come to Keyrand algorithm. So Keyrand will produce a secret key for this identity, and MS key, you know that the tableau information. Just we have to run, basically we have to generate a salted signature. So just here treat this ID as a message, generate secret key, and secret here identity secret key for this identity is nothing but signature. Just add the identity. IBIS sign. So look here first, secret key for identity just consists of ID, X, and S, and this X satisfies this equation where W is nothing but hash value of ID and S. So here signature is nothing but a proof that will make sure that signer knows this underlying secret X. Proof goes like this. So compute first run this IBIS R, mainly prove her one part to generate R many component commitment, then compute challenge. So this challenge has many component challenges. Then run for each I, and using this component commitment and component challenge, computes this response using this prover part 2. And here you can see that signature is nothing but this commitment response, and you can see the solved part as well. First, here notice that something called this nested thing is happening here. You can see that first to computing this hash value, that is the digested W, then it is again fitted here. So I mean, kind of nested thing is happening here. In the signature, if we provide challenge part, then this signature can be written as collection of many proofs of the underlying IBIS. So here each proof has 3 components. Now come to the verification. So verification given M and sigma, compute omega and challenge, then accept sigma if all the components proofs are valid with respect to the underlying IBIS. Although I did not describe this IBIS, otherwise reject. So our security proof comes in 3 steps. First, from you have no message security from WM2 problem. You have CK security from NMA security. You have CMA security from you have CK security. All are done in the classical and numerical model. And fast reduction, basically most technically involved, and it requires running adversary multiple times on some related inputs. So here we discuss mainly UF NMA security. So here is outline. Here given NMA attacker A, we will construct a wrapper algorithm B. So wrapper algorithm B basically creates the environment for A. Whenever A generates signature, B returns a special index called forking index. This is nothing but the index for Fiat Sumir oracle and the signature as well. Then rewind B with the same random tape or same random coin, but different oracles to generate 3 signature for the same message identity pair. From these 3 signature, find 3 proofs of the underlying 3 plus, and condition is that 3 challenges should be different. Then we can extract the witness by the special soundness property, and this essentially ensures that P star equal to that part of the proof system, that is the omega, sorry. Then with non-negligible probability, it can be shown that P star equal to Y star, where Y star is the problem instance, part of the problem instance, or you can say challenge. So now come to extended forking algorithm. So here first notice that there are 2 hash functions. One is involving salted UP, other is Fiat Sumir. So first question, why forking algorithm of Belare is not applicable here? So because we have to generate 2 random oracles, one of them need to be programmed appropriately to embed the challenge. And further, forking algorithm of Belare Neven requires rewinding adversary once, while we need rewind adversary twice. That is what we need to extend the original forking algorithm and weighted analysis. In this extended algorithm, we consider a special index set R. R is basically subset of N. Here phi is just a product of cardinality of the respective range of hashes. Also consider 2 efficiently computable encoding function, encoding 1 from the special index set to range of the first hash, encoding 2 special index set to range of the second hash, with some property that will require for ensuring security. And this encoding will be used to answer random oracle query of A inside the wrapper algorithm B. Now here we discuss extended forking algorithm and its application for proving NMA security. So this is the high-level view of this wrapper algorithm B. So at the end, it will provide that index and the signature sigma. So this is basically internal state. So this is a random coin, and also some other available input, that is the H1 to H new. New is the number of Oracle query. And all these H's are coming from this special index set. Also note that there is a theta, special theta, that is some special purpose that is actually programmed via this encoding function that actually connect this underlying challenge, Y star. And so inside B, actually A is run. So that means B has to answer A's query, right? So basically there are two query, H1 type of H1 queries and H2 query, two oracles. So B will answer those query either encoding or encoding 2. If it is H1 query, then encoding 1 will be used. If it is H2 query, then encoding 2 will be used. So using this corresponding, that value, random value. And further notice that, this is a signature. That means somewhere, IBIS and some other thing will be coded in the H1 and H2. So here you can see that this is the IBIS that is the kind of guess that this point actually IBIS will come, and corresponding argument for this fiat sum it has. And if guess is correct, then this quantity will be your omega, right? This quantity will be omega. Now this is the something called one done. So if you look at the only B, so if you even run B second time, something called forking. Forking means here. So up to this is same, but here you have to feed different random values. So this is called fast rewinding. So it will give you Z dash sigma dash. If you run second rewinding or third run, so again it will give you another pair. So with this probability, forking probability, all the J will be same, all the signature will be valid, and this random value will be different. So first, again, notice that all this signature is nothing but the collection of R many proofs, like pi 1 to pi R, pi 1 dash to pi R dash, and pi double dash 1 to pi double dash R. And also notice that all these signature actually agree on the same commitment, right? So, and this basically saying that by the encoding property, the challenges will be different. Then we have to choose one signature, one component proof from here. I mean, pi j from here, pi j dash from here, pi j double dash from here, with the constant that all the challenges are different. Then apply extractor to get this extra. So this essentially solves the problem, and this is the the probability bound for this solver. So that is the NMS security, you can say. And conclusion, we have proposed probably secure IBIS scheme in the MQ setting, and for arguing its security, we have developed a new forking by extending the existing one. And our forking algorithm is likely to be applicable in the security reduction of other primitives like blind signature in MQ setting. Thank you for your kind attention.
Thank you for the nice presentation. So, yeah, first again, are there questions in the room?
Is there any question? Is there any question for the talk? No, there's no question from the audiences here.
Okay, so I had a question, which is like, as you know, there's a generic construction that if you have any signature scheme, just a standard signature scheme, then it can turn it into an identity-based signature scheme with this certificate ID, right? And basically, you get a factor 2 overhead because every signature contains 2 signatures, one from the authority and one from the signer. And this looks a little bit similar to your construction, where you basically use salted LUV for the manager.
Yeah, so that kind of signature is available. Yeah, you are correct. You are correct. So that is actually by this Bellare, Neven, and NemPempty construction. So in this situation, that public key of the signature, I mean, there are 2 signature, 2 layer basically,
yeah.
And then public key of the signature will be part of the final signature. So you know that in case of this rainbow EOV, public key size is huge. So if you allow this to be part of the signature, then it will be inefficient. So that is the reason.
Yeah. So I didn't understand why. Like, what is the advantage of your scheme compared to just the generic construction?
So there's So basically, you were asking that what is the similarity? I mean, this Belare one and ours has similarity, right? You are saying?
Yes.
So it is similarity in the other sense. I mean, there is another construction of this same paper, this Belare named and Neven. So there is something called construction from standard identification scheme. So if you have a standard identification scheme and something called sampleable tableau, something called TSR, sampleable tableau relation, then you can have a such a signature scheme. But in that situation, that's that generic constant salt is not there, but our situation salt is involved. So that is what this construction will not fit in that Belare NIMPMP event construction. So that is the one reason. And other reason is that, so I mean, to argue the security. So I mean to instantiate the things in the in the MQ setting. So some security property is required, like that something called convertible standard identification as a concept. So that means that that standard identification should be compatible with the TSR, like so that something called I mean, if TSR sample something, so that will be essentially same as this signature of this underlying primitive. So I mean, actually, it does not fulfill the requirement to go through the proof. You can instantiate, but you cannot give a proof in the multivariate setting.
Okay.
Another thing I already mentioned, that is the salt part. So salt is involved. If you look at the generic construction, so basically they are just doing if you look at the something called the step n of the proof system, that is nothing but hash of ID. But here in our situation, this is hash of ID and salt. So that does not fit in their something called this tableau sampleable relation. So that is the reason.
Okay. Yeah, thank you. So yeah, that concludes the session. So thanks to all the speakers.
So thank you all the participants, and thank you for the session chairs, Professor Ward and Dr. Kusum Datta. Now I would like to request Dr. Jaiprakash Kar to say the token of appreciation to Dr. Kusum Datta, who is present at the venue. And we are very sorry that we could not manage it for the session chair who have joined remotely due to the hardship of this pandemic going on, but maybe next time. So Dr. Jaiprakash Kar.
Hello. Yes, Professor Ward, we are very, very sorry that because of in the virtually you have joined and we cannot provide the momentum.
So thanks everyone. Before we call it a day, we have one important announcement to make. For the participants and the guests who are present here in the venue, so the gala lunch for tomorrow is at 12 o'clock in the guest house premises. And then we'll be starting the next session, the invited talk by Professor Adi Samir from 1 p.m. IST sharp. So thank you for joining and have a nice day. Good night.